Good afternoon, Professor Wang, ladies and gentlemen, colleagues. Welcome to this pair seminar. My name is Qingyan Chen. I am the director of PolyU Academy for Interdisciplinary Research. And we organize seminars regularly. And today we are very happy to have Professor Iain McCULLOCH from the Princeton University to give the seminar. So now I'd like to invite Professor Wang, the Associate Vice President for Research and Innovation, to introduce our speaker. Professor Wang, please.
Dear colleagues and students, hopefully you had a wonderful holiday, and after you got immersed in delicious food, fireworks, I think now it's time to get immersed in science. Exactly 2 days ago, at the same place, at the same time, Professor George Mediras, right, from University of Cambridge delivered a wonderful talk. And today we have another quite famous professor, and Professor Iain McCULLOCH. Also, they share many common features. Both are member of Royal Society, fellow of Royal Society, fellow of Europe Academy of Science, and both worked in many different top universities, for example, in Cambridge, Oxford, Princeton, and the Imperial College, and also CAST. Okay, so today is, I think, a wonderful weather. Very, very special for today's talk. You know, the weather is very sunny. All right, the topic is harnessing the sun for chemistry. Okay, now please allow me to give very brief introduction to Professor McCULLOCH. His research involved the design, synthesis, and development of semiconducting small molecule and polymer for use as transistor for display, solar panel, and most recently, biological sensing. One of Professor McCULLOCH's breakthrough innovation is the discovery that organic semiconducting nanoparticle can act as efficient photocatalysts for producing hydrogen. This represents an invitingly new way of harnessing solar energy to generate valuable products such as hydrogen, and a sustainable way to support the growing hydrogen economy. As I just mentioned, Professor McCULLOCH is a fellow of the Royal Society, the Royal Society of Chemistry, and also European Academy of Science. His excellent research also has been translated for many products, and also received quite a number of awards. For example, 2020 Blaise Pascal Medal. I think this is a very, very famous award in material science, and also the Royal Society of Chemistry 2020 Interdisciplinary Prize. Currently, Professor McCULLOCH is an associate editor of Science Advances. If you want to submit a paper to this journal, you can recommend Professor McCULLOCH as an editor. And also, he serves as advisory board member for quite a number of journals, for example, Advanced Material and Journal of Material Chemistry C, Material Advances, and also Material Science and Engineering R report. The impact factor, I think, is 26 this year. Without further ado, ladies and gentlemen, and now let us give a warm welcome to Professor McCULLOCH.
Thank you very much for that lovely introduction. Oh. Okay. So yeah, this is actually my second pair talk this year. So I came in the winter of this year, and I had a discussion about electrochemical transistors and biological applications. Today, I'm going to talk about one of the big motivating factors in science, and that's energy. How we can decarbonize energy, how we can make chemistry more sustainable. And actually, I was going to just complement the previous slide, which did a really nice little cartoon. I haven't seen that before. It's really pretty. But seeing how the sun generates hydrogen on the other side, that was really cool. So this is what I'm going to talk about. But at the very beginning, I'd just like to, for the students mainly, I would say, is to just go back and try and put, well, the motivation for this in a little bit of context. You know, the planet's warming up, and it's warming up because of carbon dioxide in the air. And that's a fact. That's not my spin on this or any kind of prejudice that I have. Climate change is definitely here. And we have to reverse this problem of burning fossil fuels. For a variety of reasons, it's just not sustainable. So how do we electrify energy, and how do we make it clean? So that's really the motivation that I have, and I'm going to start with showing what I mean by that. So if we just look, it's pretty alarming. This is the consumption of energy as a function of time from the 1800s, and you can see, you know, around the Industrial Revolution, it starts to dramatically rise. We're using an awful lot of energy now. As the world's population grows, as industrialization continues, as urbanization grows as well across the world. And also, if we look, this is 2021 data, you can see predominantly fossil fuels are used to generate energy. This is a small amount of biomass. Coal is quite a large fraction. It's a bit alarming. Oil and natural gas. So you would say like about 80% at least, 85% of our energy is from fossil fuels. However, on the bright side, if we look to new installations of power generation, so power plant installations now, it's a little bit of a different picture. So actually, if we look at 2021, almost half of the world's power generation is actually solar. So 48% at the moment globally of new power installations is from solar technology. And actually, if you look into the cost of electricity, so if you think about the unit of measure or the parameter of interest, I'd say it's kilowatts per hour. And solar is almost free. It's less than a cent per kilowatt hour in Abu Dhabi right now. It's about 1 cent, which is incredibly cheap. So solar energy is competitive with all these other technologies. It's just a matter of now being able to electrify a lot of processes. So, and of course, the other problem with solar I'm going to discuss a little bit later is the intermittency issue. But back to the problem. So we are still using fossil fuels for about 85% of our energy, and you can see the implication of that on carbon dioxide. So if you look again historically in parts per ppm, parts per million of CO2, you'll see this dramatic rise at the start of the Industrial Revolution. The steam engine in particular really catalyzed this. So this is data, this is not an opinion. You can see dramatically the rise of CO2 in the air due to burning fossil fuels. And CO2, if you're a chemist and you want to do chemistry with CO2, I'm going to show one graph later on what we're trying to do to valorize CO2. In other words, increase its value, do some chemistry on it. Very difficult. It's a very stable, thermodynamically stable molecule. Once it's in the air, it just stays there. So what we see now is the cumulative effect of the last 100 years of CO2 emissions. They're still there. So we're just adding to this. And so we need to try to reverse this. And so why do we need to do this? Well, let's have a look at this graph here, which is another really alarming graph. So this just shows the effect of global warming. So you can see quite clearly, almost everywhere on the planet is a kind of red color. That means over the last 5 years, the temperature has increased up to like 1-2 degrees. So in most parts of Asia, you'll see there's been a 2-degree rise in temperature. And if this happens, of course, in glacial areas, there's going to be a corresponding rise in the sea level. And that's going to affect us all over the world. So again, this is data. It's pretty alarming. And I think now is the time we have to look at this for the next generations and try to reverse it. So what can we do to shift away from fossil energy? So if we look, this is an energy flow diagram, and you can see today, petroleum, natural gas, coal, and a bit of nuclear are the primary sources of energy. And so where's it being used? It's being used in residential, in buildings, industrial processes, and transportation. And it's roughly a third. Transportation, marine and aviation are particularly hungry for fossil fuels. And you see petroleum is primarily used here. So electrification doesn't really reach at the moment transportation. Very little reaches industry. There's a little bit in buildings, obviously. The big consumer of energy in buildings, it will be, for example, heating and cooling. So how do we make buildings more energy efficient is also very important. But we see this transition, this electrification, this decarbonization hopefully occurring over the next 30 years or so. And you can see now that there's a pretty broad mix predicted for 2050. And, you know, this idea of net zero by 2050 that we all signed up for in the Paris Agreement, it's not on track and it's not going to happen. And I think it's not even being really taken seriously anymore globally. That doesn't mean we don't work on it, but I think we need to be realistic about the mix of energy that we have. And we can still burn fossil fuels if we have some type of sequestration and storage option along with it. So these will be, this is what we predict is going to happen. There'll be quite a lot of nuclear. Nuclear for these small modular units for AI, for example, are really taking off in the US again because AI is incredibly energy intensive. A single search on ChatGPT consumes about 10 times the amount of energy as a Google search, for example, and ChatGPT is getting more and more widely used. So we need to pay attention to this. Where do we see options for solar, for wind, all of these renewable energy potential? So this is where we're trying to get involved, in particular in solar, and then being able to capture and store energy created by solar from hydrogen. So that gives you some sort of idea of the motivation here. And why solar? Well, if you just look at a very simple picture here. So these are the reserves. So this is on a terawatt basis here. These are the reserves on the planet for a lot of different fossil fuels, so coal, oil, natural gas. And the yellow cube is the solar irradiation in 1 year. So this is not the cumulative amount that's available. This is per year. And you see it dwarfs all other possible sources of energy. So we really need to be capturing this more than we are at the moment. And this, I think, quite nicely sums up why we want to do that. So the problem with solar, or one of the issues about solar, obviously, is it just transfers solar irradiation into electricity, and it only happens when the sun shines or when there's irradiation. So in other words, in the evenings, there's no supply of solar, and it's also intermittent on an annual basis. There's more solar in the summer and less in the winter. And batteries can't really address these long-range cycles. So we need to think about other storage techniques where we can take advantage of the points in the day when there's more supply than demand so that we can store, and then use that when there's more demand than supply. And hydrogen is one potential option here. Not the only option, and there are other reasons why hydrogen is a very important commodity material in industrialization in general, and I'll come on to that. But it's a very interesting opportunity and potential. So if we think about all shades of hydrogen, gray hydrogen is when you're just cracking a fossil fuel and the CO2 is getting pumped off. There's blue hydrogen when there's carbon storage, when you generate hydrogen from fossil fuels. We're interested in green hydrogen, and that's hydrogen that's generated from water, either through electrolysis or photolytically. At the moment, it's a very, very tiny proportion of hydrogen that's green. Most of this is grey still, coming from natural gas and from oil. So we get our hydrogen from hydrocarbons. It's very inefficient and it generates a lot of CO2. So this is not sustainable. Where's it used? Well, if you don't believe in a hydrogen fuel cell to drive your car or a hydrogen aviation, we still need it in a lot of industrial products. So for example, ammonia for fertilizer, Haber-Bosch process, we need hydrogen for that. We need hydrogen in order to reduce iron ore to make steel. These are huge opportunities for hydrogen and requirements, and we want to make that green now. To alleviate this catalytic cracking that generates all this CO2. So even if you don't believe in hydrogen as an energy carrier, and there are reasons why it's a challenge. It's very hard to compress. It's not volume dense energy. It's very weight. It's excellent in terms of its energy per weight, but not its energy per volume. Transferring it or somehow storing it at 700 bar to liquefy it is also an engineering challenge. But there are ways in which we're thinking about maybe converting it to ammonia and other things. And actually, in Singapore, there's marine transportation that's running on ammonia as a fuel, which is quite interesting. So it's circumventing its reformation into hydrogen and just burning ammonia directly. So there are lots of opportunities where we can use hydrogen. So now comes to a bit of science. Hopefully I've convinced you that there is a lot of motivation for hydrogen as a material for industrial processes and for energy. So how do we try and make it? Well, one area that we've been very interested in is not electrolysis, but photocatalytic hydrogen production. So in other words, taking advantage of the semiconductor properties of a material, creating excited electrons and excited holes, and driving electrolysis, an electrolytic process. So here you can see we have our material here. Light is incident on it. We generate these excitons. This is an organic material. In an inorganic semiconductor, we generate immediately free charges. And these charges can then migrate to the co-catalyst where the chemistry happens. So these electrochemical reactions happen in the presence of water. So water split to hydrogen and oxygen, and we get this gaseous evolution. And actually, it's a lot easier than you might think to actually be able to separate the hydrogen from the oxygen. We can do this with common membrane technologies. And so this process works quite well. The key is to make it cheap enough. And this is where the photocatalytic nanoparticle opportunity, I think, is very opportune. It's probably the cheapest potential way in which we can do this. So if we look a little bit more into the properties required from a semiconductor in order to drive these electrochemical reactions, you can see this quite clearly here. So this is a wide bandgap semiconductor. As I mentioned, light is incident. It promotes an electron, from your valence band, if you're a physicist, to your conduction band, if you're a chemist, from the HOMO to the LUMO. And somehow we're generating free carriers, or they're splitting at this heterojunction with our co-catalyst here or here. And then we can drive oxidation and reduction. And you need a minimum band gap of 1.23 electron volts for this process to occur. And I say that as a minimum band gap because these processes have a built-in overpotential. So you actually need closer to 2 electron volts in order to efficiently have enough thermodynamic drive to, because this is a 4-electron process. So you need quite a lot of overpotential to drive the oxidation reaction, a little bit less for the reduction. But nonetheless, when you start to consider 2.5 electron volts to drive this process, and you realize the most abundant part of the solar spectrum is around 1.4 electron volts, there's a real mismatch there. So most of these inorganic semiconductor materials, your titanias, etc., that are used, they're only capturing a small fraction of the available spectrum. So that's really not enough. If we want to be driving this process efficiently, we want to be capturing more solar irradiation, more of the red and infrared parts of the spectrum, not just the UV. So we were looking at organic semiconductors as a way to make nanoparticles. And I guess maybe 10 years ago, this was just beginning. There was some groups that were developing wide bandgap organic systems. And there was some problem. They still have this mismatch between the bandgap and the solar irradiation abundance. But also, a typical semiconductor, organic semiconductor, it's quite hard to make nanoparticles less than about 50 nanometers. So if you have a 50 nanometer nanoparticle, the typical maximum exciton diffusion length within an organic semiconductor is around 5 to 10 nanometers. So what that means is that any excitons that you're forming in the middle of this nanoparticle, they're never getting out. They're never generating free charges. So what happens is they'll just geminately recombine. So you're not being able to harvest any of the light to create charges. So this is a parasitic part, dead volume in the middle of your nanoparticle. It's not taking part in the chemistry, and it's parasitically taking light away from the rest of your materials. So this was the problem that we faced when we started working in this field a few years ago. So what we thought was, so my background at this point was in organic solar cells. And organic solar cells have solved this problem already. So what they do in an organic solar cell in order to generate free charges is to create an internal heterojunction. So an offset in energy level between two components that allows a thermodynamically favorable charge transfer process, either an electron transfer or a hole transfer, in order to create free charges. And that's how solar cells work. And you sweep these charges due to an internal field. In a nanoparticle, of course, we don't have an internal field. So we require drift of our free charges to get to the co-catalyst, usually platinum, on the surface. But when we started to think about this, well, we thought, well, maybe there's two types of two material particles that could maybe occur. One would be this so-called core shell type nanoparticle, where you've got a donor acceptor, and it can either be in the core or in the shell. And we thought this would probably be the most common, because typically two components have different surface tensions, different surface energies. So one would be preferentially radially driven to the surface, as in a nano emulsion technique. And as the nanoparticle dries from solvent, one of the components would preferentially go to the surface, just typical thermodynamics. The other, of course, is if the two phases just randomly separate into what we call an intermixed nanoparticle. So I'd been working on a bunch of non-fluorine acceptors. This is one from our lab here, IDTBR, and we thought we'd combine them with a typical organic solar cell donor. We're not trying to reinvent anything here. We're just basically taking materials that exist already in a solar cell application and seeing if they work in a nanoparticle. So the way that we make these nanoparticles is so-called mini emulsion technique. So we create this emulsion with surfactant. Usually we have water as a dispersion, and we dissolve our two components in chloroform. And we use a typical surfactant here. This is SDS. You've got your long fatty tail and your ionic head. And so when we look at the interfacial tension, of course, this is chloroform and water. It's a very high interfacial tension. And when you add your surfactant, of course, the interfacial tensions drop. That's what you would expect from a surfactant. But when we look at the difference here, you'll see that when you add your surfactant to your non-fluorine acceptor, we have twice the interfacial tension as we do when we have our donor polymer. So this is a lower interfacial tension. So when you just think about that, what would you expect to happen? Well, thermodynamically, you would expect the lower surface tension material to go to the surface preferentially. So we would have expected to have EHID TBR core with a PCE10 shell. So that's what we thought would happen on the basis of a very simple effect of interfacial tension. Of course, there are other effects due to solubility and spinal effects that can happen as well. But on a very first pass analysis, that's what we would expect. Oops, sorry. And that's exactly what we see. So these are cryo-TEM images of our nanoparticles. Not much to see here. This looks like a fairly amorphous nanoparticle. Here, this is EHID TBR, and hopefully you can see that. You can see some beautiful organized lattice fringes here. This is a perfect crystal. And one of the reasons it forms such nice ordered structures is that in comparison to spin coating, when you make a thin film by spin coating for a solar cell, that's a very quick, rapid kinetic process. Solvent flashes off and you get the kinetically frozen product. Here, this takes a little bit longer. So there's more time for nucleation and growth. So you get very highly ordered structures here. And when we make our binary heterojunction nanoparticle, it's exactly what we would have expected. We've got our EHID TBR core, and on the shell here, we've got the amorphous PCE10. So this is exactly what we'd expect. And then when we look at, so this is the heterojunction of our donor and acceptor, and they were chosen deliberately to have band gaps that match the solar spectrum and a nice energetic offset in order to generate free charge carriers, electrons and holes at the interface. So this has already been well studied in OPV, and we know that this system works. When we look at the energy levels for oxidation and reduction, we can see a couple of things that stand out here. Firstly, the energy level of our excited electrons in the acceptor should be still sufficiently offset thermodynamically in order to drive this proton to hydrogen reduction. So this is a thermodynamically favorable process. However, when the hole was transferred to our donor, you now see that this is a thermodynamically unfavorable situation with regards to water oxidation. So what we do instead of water oxidation, we have to add at this point a sacrificial oxidation agent. And so we add ascorbic acid, and this is an oxidation process that has this potential here. So we know that our holes on our donor are still sufficiently active to drive this ascorbic acid oxidation. So it's oxidized to this diol, the ketone product here. But the problem that we can see with this core shell approach is, okay, once we transfer our holes to the shell, that's all very well. It's very nice. We've got our potential for oxidation at the surface. But the worry here is that the electrons that we have on our AHID TBR, they're buried in the center of the core of the nanoparticle. So that's not really a very efficient setup for the reduction reaction that occurs with the platinum on the surface of a nanoparticle. So this was a worry. And in fact, when we look at the hydrogen evolution, it's actually pretty good, the mixture. But we can see here, we need to have the maximum ratio is about 90% of the acceptor and only 10% of the donor. So that's not a very good situation for efficient exciton splitting of both donor and acceptor. So that's a worry. And we can see here, when you look at the Herr rate, that's a hydrogen evolution rate versus a fraction of EHID TBR, you really need to be up around 90% to get this maximum Herr. So when we think about that, what we think happens here at this very high acceptor, it's kind of poking through the shell in order to allow very thin donor shell that allows electrons to be able to reach our platinum. But, you know, probably not ideal, because this maximum at 90%, it doesn't really match efficient exciton dissociation. So if you look at exciton quenching efficiency of the donor and the acceptor, you'll see that ideally for a solar cell combination, you want to be around 50%. That's 50, 60% is ideal for a solar cell. In our case, the maximum Herr rate is at 90%. So that's really inefficient here for our exciton dissociation of our acceptor. So this setup is not really delivering the charges that we'd like to see. And as a result, you know, the Herr rate at this point was better than anything out there. So we were quite happy about it, but we thought we could do better. So we started to think, well, how do we try to get a system where there's no preferential radial segregation due to basic thermodynamic considerations? How do we try to find a system where we have the same interfacial tension for the donor and the acceptor? So we looked around and we found this, call it a surfactant, but you can see the interfacial tensions are pretty high, right? So it doesn't really work particularly well as a surfactant, but we have our head and a little bit of a aliphatic tail. But the interesting thing here now is that there is a difference in surface tension between our donor and acceptor when we add the TEBs, but not much. Remember, in the previous case, it was twice the interfacial tension for the acceptor and the donor. Here, it's maybe a factor of 10%, not that much different. So now we're expecting less radial segregation. So there's the opportunity, if we get phase segregation, that it can be quite random around the particle. And indeed, that's what happens. You've seen the PCE10 and EHID TBR particles before, but now we have this intermixed morphology. We've got small crystalline domains. You might be able to see a domain here. You can see another one here. There's a little bit up here and something down here. So, and these are randomly oriented. So this is not the same crystal. So we've got a well-dispersed, intermixed morphology. So this is very different from the previous system. Again, we've got this nice energetic offset. It's the same material set, so this is exactly the same. But now we have the opportunity for both electrons to find their way to the surface and holes to find their way to the surface. So we've got the best of both worlds here. And in fact, that's absolutely what we see from the Herr rate. So you can see here, the maximum rate is when we have something like a 30-70 or even less ratio of the donor and acceptor. So it's now no longer a way up here at 90%. We've shifted that to around 70%. So exciton dissociation can occur at the interface of donor and acceptor throughout the nanoparticle. And the other thing of note here is the Herr rate. This is an order of magnitude larger hair rate than when you have the core shell nanoparticle. So having this intermixed morphology where we're creating all these free charges that can then directly diffuse to the surface and undergo both oxidation and reduction reactions. You can see here that this is a very efficient situation. And these numbers were very, very high at the time because this wasn't really done in the literature. And you can see that this is our EQE as a function of in the visible, not dramatically great, right? So we really need to get this up. So the target is for hydrogen evolution is roughly $1 a kilogram. You're not going to achieve this with EQEs over 2%. So we still need to increase this a little bit. But if you compare it to the conventional technologies, this was the best polymer that was out there. This is carbon nitride and this is titanium. So these were the two benchmark materials. And you can see that our heterojunction dramatically outperforms them on overall hair rate, but also maybe more importantly, hair rate per milligram of platinum if you start to think about the cost and the use of rare earth metals. So we were able to deliver on that. So we started to, investigate different compositions in order to try to drive this the charge generation better. And what we noticed actually, which kind of surprised us, was, well, if you have this intermixed morphology, it looks good, but you don't even need to have that as long as you have something where what we call broken core shell. So hope you can see this here. This is a very nice illustration of our shell PM6 donor. It forms these concentric lamella, and then we have a more amorphous core. This is PCBM. Interestingly, you'll see that the platinum, this is photo deposited, only deposits on the acceptor. So if you want to know where your acceptor is, you just look at a photo deposited nanoparticle, and you can see quite clearly it's not forming on the donor at all. So this is a broken core shell here and here, but only on here. And when we compared this to our previous paper where we'd reported quite high efficiencies, we beat this easily with this broken core shell morphology. So it was a little bit embarrassing because, in our previous paper, we've been saying you really want to have this intermixed morphology. And now we're saying, well, maybe not actually. And if we look to see what's happening here, one of the important things is if you look at this PIA spectra, you'll see that you get this charge generation. So this is the PM6 polar ions. And once you stop the radiation, these charges persist over a time scale of seconds. So we are able to really access chemistry. Organic chemistry occurs at that time scale. It's not that if the lifetime of your charges is in a microsecond scale, you're not going to be able to do a lot of chemistry with this. Another thing is that when we look at the intensity of this the PIA spectrum, we can calculate we've got around 600 charges per nanoparticle, so 10 to the 18 per centimeter cubed. This is much, much higher than the maximum you'll ever see in a solar cell. And that's quite an interesting thing. And so why is this? Well, we think it's because these nanoparticles are in water, and this water on the surface stabilizes the charges, high dielectric constant. It screens and stabilizes these charges so they can persist for a long time, and they're really highly dense. So this is, I think, quite an interesting observation and quite unusual. And you can see how we do very nice PL quenching of our material. So we can see that we've got very efficient extern splitting. So what's going on here when we look at these two situations? Well, this is our broken core shell. And what's good about that? It's a very simple system, right? We've got formation of our exciton. At the heterojunction, we get the splitting here. So we get our free charge carriers. Then our free charge carriers drive the chemistry. A little bit more complicated in this intermixed structure. So if you imagine a situation where we have an isolated either donor or acceptor buried in the center of our nanoparticle, there's no way that these charges are getting out. And it's particularly important for electrons. So if you've got an isolated acceptor domain here, this is a problem, and I'll show you the implications of this later. But here, this is an example of a really nice core shell particle. You see these beautiful concentric images here, hopefully, and then we have more amorphous part here. Here we've got our intermixed structure here, and we can look at this at the periodicity of the lamellar fringes here. You see very nice uniformity, and here are two distinct features of our donor and acceptor here that we can see when we look at the images. And well, what we can see firstly is that when we have this broken core shell type structure, firstly, we get much higher photocharge generation. So we see this from the PIA spectra, much higher hair rate. So these are three donor acceptor systems that form broken core shells, and these are three that form intermixed. We see the hair rate is much lower in comparison to these systems. But really interestingly is that the three low hair rates are also degrading much faster. So you see this degradation over, I think this is 24 hours, constant irradiation. And the reason for this is that most organic acceptor molecules are unstable in the presence of excited electrons. So if you generate an excited electron in the middle of your nanoparticle, it's not getting swept to do good chemistry on the surface. It's going to undergo some type of degradation process. And this is well known, particularly for Y6. So we're starting to realize now that we need to have a really nice demixed system to get almost like what I'm calling broken core shell. You might also think of it as a Janus type particle, like 50-50 separated, which looks really quite interesting. Well, I'm just looking at the time here. I think I'll try and go fairly quickly through the last few slides. Lots of other things we've looked at here. I mentioned earlier about this stabilization of charges. You can see this. This is a relative permittivity of a glycolated, this is a glycolated donor. This is IDTBT. But when you glycolate the side chains, and they swell in water, so the water uptake leads to a very high relative permittivity. So in other words, dielectric constant is increasing. When it increases, it stabilizes the charges and helps separate them. So this is a very interesting system. So having this glycolation, again, we can see this really rapid. If you compare non-glycolated and glycolated transient absorptions, firstly, you can see that the intensity of the absorption is much higher, but also that the decay is different. So this is a geminate decay. So this is fluence-independent decay. So when we look at the decay as a function of radiation intensities, it's pretty similar. And that tells you that the recombination occurs within the same exciton, so it's geminate recombination. In the case of our GIDTPT, it's a bimolecular recombination. We're forming more free charge carriers, and the way that they recombine is bimolecular processes. All right, 5 minutes left. Other things that we've been looking at are COF materials. So COFs have a couple of advantages. One, they've got a lot of internal free volume. So if you want to be able to bring in some moieties for chemistry, water, whatever you want to do, you've got a lot of internal surface area. So this is a pretty good system for photocatalysis. And we worked on templating donor acceptor COFs together. So this is work by Kath Aitchison, who's now in Linköping. And you can see we make this acceptor, donor, acceptor sandwich. It actually took a lot of work to be able to do this. You start with your donor template, and it only really works when you've got a topological match between the donor and the acceptor. So what that means is it means that the ring size has to be exactly the same. Otherwise, you get no free volume. You've just closed the pores down. And you see when you have this topological match, we are able to drive our chemistry quite nicely here. When we published this paper, actually, it wasn't rejected, but the reviewers didn't like the fact that we were calling this a cough, because if you want to really demonstrate that you've got cough material, you have to show by the X-ray a really, really strong reflection due to long periodicity. So this was what we call a 2D network type material. But eventually we were able to make coughs with this type of structure. And you see now, we finally get to see, and these are the first materials, the ones that we published. We actually haven't published this, but you see there's no really strong reflections. Here we see a very strong reflections that matches exactly the internal diameter of our surface. So we've definitely got a cough in this case. And they have higher hydrogen evolution, as you'd expect, than the 2D structures. I think I have a couple of slides left just to say that you don't need to have a cough to generate internal porosity. You can use the type of simple spiral techniques to get these, what we call polymers of intrinsic microporosity. They also have high internal volume. So we played around with a bunch of these. The take-home message here is, yes, if you have this internal porosity, you can drive a more efficient photocatalytic process. But the key really is not the porosity. The key is the hydrophilicity. So if you want to bring water into your nanoparticle to do the chemistry, it's not enough just to have a pore. It has to be a hydrophilic pore. So the combination of this material has got both high internal porosity and hydrophilicity, and this has by far the highest Herr rate. If you can drive the reduction of a proton, well, what else can you do? Other things we've been doing with what we're calling metal covalent organic frameworks. It's not a MOF because our cobalt complex is covalently included in the structure here. You can see very nice periodicity, quite good internal BET surface here. So it's definitely a lot of internal porosity. In this case, we've been able to demonstrate quite effective CO2 reductions. I think this at the time was one of the highest examples of CO2 reduction to CO out there in the literature. And with that, I think we're pretty much on time. Hopefully I've convinced you a little bit. Sorry for being a little bit on my soapbox about climate change and energy and sustainable materials, but I think it's a really important topic to work on. And hopefully I've explained to you why I think that is. Organic photocatalysis is pretty new. I think it's something that has a lot of potential, but we have a ways to go. And I think that's really exciting from a research perspective. And I will stop there. Thank you very much for your attention. I'll take any questions. Thank you.
Okay, so the next session is for Q&A, and the chair from the Department of Applied Physics. So yeah, very nice talk. Thank you very much. So now it's open for questions. Any questions from my audience? Yeah, please, George.
Thank you, George. Yeah, thank you. Any comments on the stability of these materials?
So here's one example of the degradation, so instability. I don't think this is one. So if you look at the bottom, can you see that the bottom right hand? Get to your question as well. So if we look here, you can see this is the percentage degradation. That's not very encouraging, is it? Thank you. Is it possible to get something to? So here you can see this is
there.
this is pretty unstable, right? So this is 60% is degraded in 24 hours. Here we can really reduce this, and the way to reduce this is to eliminate isolated, excited electrons. So that's what we have to do. If I go back, so if you look at this, don't know. So here's another example here. Now, if this was perfectly stable, you would see this would be a straight line. You see this roll over that starts to occur in 10, 12 hours. It looks bad, but we think one of the reasons for this is actually the availability of the sacrificial oxidation. So once you deplete it and there's no more left, the rate starts to drop. So this is not only due to degradation, but it's due to lack of the sacrificial oxidation agent. I don't think this is working. So there's lots to be done. Eliminating excited electrons, I think, is the key for that.
Yeah, please.
Hello, Professor McCULLOCH.
Hello.
I thought you may remember me. I'm Yu Han from Professor He Yan's group. Yeah, and now I'm practicing as AP assistant professor in the ABCT of PolyU.
Nice.
And yeah,
congratulations.
Yeah, it's a long time we haven't met each other.
That's right.
And I have learned your work for a long time. Yeah, from my PhD degree of 2020. And
you make me feel very old.
Yeah. Yeah, and now I'm still focusing on the semiconductor material for OPV.
Oh,
so
right.
I'm just wondering, you mentioned the first part of your work is a DA blend for the photocatalyst, but in the following work is focusing on some single component or N-type materials. I thought.
I would say no. All of this has two components.
I mean the IDTBR glaciers, that one based.
This one.
This one is based only one.
Yeah.
It seems the only single component. So I just wondering whether it's mandatory condition for this photocatalyst system to use a
single
component or N-type single component or a DA blend.
Actually, this is a donor acceptor. This has got an IDTBR core. See that beautiful lamellar structure here? And the core is round the side of it. But the photophysics is on just the single component. But the actual hair rates are, as you can see, IDTBT, IDTBR. So this is also a donor acceptor system.
Okay.
And here's this, well, the single systems. The single systems do work because if you think about it, they only work for acceptors. So for example, Y6, Y6 is a bit of a mystery for everybody, right? It was developed now, I would say 10 years ago, maybe, and still is the #1 molecular skeleton of choice as an acceptor in a solar cell. It's crazy that 10 years later, it's not been improved upon. And the reason I think for that was at the time it was invented, nobody knew why it worked. Why was it better than the other non-fluorine acceptors? But I think one thing that Y6 seems to do is that it seems to generate free carriers. So one thing is it has a long extern diffusion length, much more than the typical non-fluorine acceptor, but it also internally generates free carriers. So Y6 as a single component nanoparticle works pretty well.
Yeah.
The heterojunction there is the platinum co-catalyst.
Okay.
So that's all. If you have an acceptor like Y6, it generates internally free carriers, and you then have your heterojunction at the platinum, it can work pretty well.
Yeah.
But a donor acceptor combination, in theory, can have more of a panchromatic absorption. So you're able to absorb more of the solar spectrum if you have two components than one. So I'm not sure why you would want to just have one component when two gives you a theoretical benefit. But you can be, these tear rates are much lower for a single component. I don't know why we never published single components. Maybe there has been some papers out
Yeah,
there.
there's a lot of publication, especially for the mainland China research community. They publish a lot, focus on just the Y
think
series.
the Y
acceptor.
series,
Yeah, only
yeah.
single component. Yeah.
Yeah, but I think a donor can allow you to access more of the solar
More
spectrum.
efficient, yeah,
I
dissociation,
think
yeah.
so, yeah.
Okay, thank you, Professor.
Thank you.
Professor Wang, please.
Thank you very much, Ian, for the wonderful talk. And
Thank you.
particularly, I think I'm very interested in the organic semiconductor you're using for photocatalyst. I have been working on inorganic photocatalysts for nearly 20 years.
You have?
So, yeah.
Oh,
So, it's
so you know much more about it than me, I'm sure.
No. It's very nice to see. I think a new group of catalysts can also work very well. But I think we have been struggling to increase the EQE, for example, the quantum efficiency, particularly in the wavelength of 500 to 700, and you can achieve, say, 5-6%, and which is very impressive.
Yeah.
But in the lower, the stronger wavelength part, I think, so like the strontium, titanate, titanium, they can do a bit better.
They do.
Yeah.
So, but if I just look here, so actually, you know, this system is getting better. The first system was around 2-3%. You can see across the visible range.
Yeah.
I mean, 8.7, or take the point with a bit of salt, but roughly 9% to around. This actually, 3% when there's not a lot of absorption.
You also have one result showing better than this one, yeah, and the first one. That's it.
We have better than this, but I don't think I'd showed it.
Okay.
I think that's in a manuscript that's getting submitted quite soon. Actually, this one was worse. So this was the other one I showed. But yeah, you see that when you've got more absorption here. So it's related to not only to the absorption, but the ability to extract the charges. So if the charges are recombining, of course your EQE drops. And we're still figuring out the best morphology. When I showed you that at the end, that's the way to get higher EQEs, and we can get into the double figure EQEs across
that would be very
spectrum.
good.
Yeah, but George asked a very nasty question about the stability, and that's true. So I mean, 10% EQE is good, but you also need to have a lifetime associate if you want to really. So this nanoparticle approach could be really interesting for portable remote locations where there's no electricity. If you have electricity, then electrolysis is probably as good an option. Right? It's more developed. So to get this effective to be commercial, I think you need to have the 10% EQE across most of the solar spectrum, and then also to have appropriate lifetimes. I'm not sure what that would be, but certainly in excess of 10 hours, right? You need to be at the months, depending on the cost, right, of your product. So the lower the cost, the shorter the lifetime, you could probably be acceptable in the market.
And a follow-up question on this one is, so because you using some, I think, acid, yeah, and like sacrificial agent.
Yeah.
So because in doing this way, it's like a sort of a downhill reactions, and if you do the overall water splitting, for example, without any sacrificial agent, you split water to produce hydrogen and oxygen is uphill one. Is that possible to use your new catalyst to split water, overall split?
So we can do this now. We haven't published this, but we are able to. So oxygen evolution is actually quite tricky. And if you look at the papers that have shown it, after the talk, I'll show you our data. So we have this now. But it's very difficult, and the problem is that the literature is not helpful. And the reason the literature is not helpful, if you look at every organic photocatalyst that's in the literature, the typical irradiation intensity is 5 suns. Who's got, I mean, we can't even get to 5 suns in our lab. It's a hazard, right? So that's not reasonable. And the EQEs are so low that you have to monitor the nitrogen along with the oxygen. Because if your oxygen is coming in from leaks in your system, then you'll see this sort of the ratio of oxygen to nitrogen won't change. You need that to be independent of the nitrogen increase. So we're only now we're starting to develop structure property relationships around these materials. And what we're finding is it's quite easy to have a material. So this is the heterojunction, right? So if the hole is down here, then theoretically it can oxidize water, but you need, I would say, about a 0.4, 0.5 over potential. So you need to have a HOMO energy level of almost 6 electron volts. Hard to actually measure that by UPS because it's so deep. So you need a very deep HOMO, and then you need a co-catalyst like cobalt. And then your oxidation, your reduction catalyst, some sort of silver catalyst or whatever, you need to be able to have all this in combination. So it's not straightforward, but it's definitely doable, and we've been working on that now.
Thank you very much.
Thank you. So any other questions?
Yeah.
Yeah, please.
Hi, Ian. Nice to meet you again.
Hey.
I attended a talk a few years back in AP. I'm Ben Lo from ABCP and AP as well.
Hi.
I got a general question because you shifted from nanoparticle, core shell nanoparticle to intermix nanoparticle, and then all the way to this type of intermix COV or covalent network structure. Considering you are working on photocatalytic hydrogen production, right? Have you? So the stability problem is really a big problem in this sort of covalent structure or framework.
In the frameworks, yeah. Yeah, okay.
So do you have any suggestion how to address this type of stability problem in more COV structure when you're working on photocatalysis? Because it's really a big problem in the field.
Well, I mean, the first thing is like to really identify what we mean by instability. So when I show a slide like, sorry, I'm going back and forward here, this one. This doesn't really help. Degradation 60, 70%. What do we mean by degradation? What we're saying here is that this is a UV absorption data. So 70% of the absorption or the extinction coefficient is gone. But where's it gone and what's happened? So I think we need to understand, firstly, what are the sources of this instability? Is the instability just material fragmentation? Is it photo bleaching? Is there actual chemistry going on? And we're trying to do this now. So one thing that we can see is that with most non-fullerene acceptors, if you trap an electron and there's no way for that electron, an excited electron, and there's no way for that to reach the co-catalyst on the surface, the likelihood is that's going to undergo some unwanted chemistry that leads to degradation. So simply, if you have a demixed system, like a broken core shell or a Janus type structure, you reduce the isolated electrons in your acceptor, and that dramatically improves the stability. To what degree, we're still working on this, but we know that that's a step in the right direction. It's like everything else. If you look at perovskite research 10 years ago, it was a mess, right? But slowly, we start to see, well, maybe the interface is a problem. Maybe we should replace formidinium with cesium. All these little sort of iterative improvements that go on time by time. This technology is pretty new. I think that the key to commercial success will be to find a sweet spot in the application versus stability. It's not going to give you 30-year lifetimes. Organic solar is not going to do that for you either. And the charge densities here are much higher than in a solar cell. So the opportunity for chemistry also is much higher, which can be good and bad. So we need to probably improve the stability dramatically, but then we probably have to find short lifetime applications just like in solar, the disposable type application.
Thank you very much.
Okay, so actually, I also received several online questions from registrants. So one question is about the future of this green hydrogen, considering the support of AI, where green hydrogen become a dominant energy source in 10 to 15 years. Do you think it is possible?
Well, I hope I made the case for hydrogen. If I go back, maybe if I can go back to earlier slides. So people have been very negative in the last 2-3 years about hydrogen, I would say, as a technology. Oops, there we are. Because they're only looking at this down here, this sector, transportation. So fuel cells have not delivered. Almost every major car manufacturer is pulled out of hydrogen as a fuel source. All kinds of engineering-based reasons around that being a problem for fuel cells. Only Toyota, I think, are left. And Toyota have bet big on hydrogen, but it's still not getting there. But I don't see, this is a small sector. You know, if we want to feed the planet, we need fertilizer, and we can't crack fossil fuels to make hydrogen. We need green hydrogen in order to satisfy a lot of industrial processes. If we want to decarbonize steel manufacture, you look around Hong Kong or anywhere in China, you know, the amount of building work that's happening, the amount of construction, cement is another, you know, to get rid of blast furnaces for making Portland cement, go into either an electric arc or some type of hydrogen burning. That will dramatically decrease the carbon footprint of cement. Cement, as you can see, the amount of cement that's used, cement and steel, both very carbon intense industries. So we can replace this. I also feel like even if hydrogen as a fuel source doesn't commercially deliver, the fallback of ammonia is quite an interesting one. You know, ammonia is being used in Singapore right now in marine transportation. So for heavy transportation, long haul marine transportation, batteries won't do. We need to get away from fossil fuels. So ammonia is actually a very promising option.
Okay, thank you. So actually, yeah, I also have a question.
Sure.
About this new technology. So the generation rate, hydrogen generation rate is related to the surface area, right? So you see, how can you control the nano size of the nanoparticle so to get a more efficient?
That's an interesting question. And I don't have a good answer about what. So we call this a Goldilocks scenario. So when the nanoparticle size is very, very small, you still have to, then there's a lot of particles that don't have any platinum on them. It's hard to photodeposit platinum onto very small particles. And also when you do, then the ratio of platinum to particle size is quite high. Platinum shields the light. So there's not a lot of irradiation. So if you've got very, very small particles, it's hard to deposit. And when you do deposit, you don't get access to the spectrum. So we get this, what we call Goldilocks effect. Around 50 nanometers, you've got an opportunity for exciton splitting and free charges reaching the surface. So that's a good size. When it's too large, obviously in the center, you get the dead zone. So you split charges, but the boron diffusion length is not large enough to get to the surface. So we see this optimum size being around 50 nanometers or so. It's also very hard to stabilize very, very small particles. You need I haven't really said anything about this, but even at 50 nanometers, we say we use a surfactant, but when people talk about surfactants, you talk about a weight ratio of 0.01% or something. Our weight ratio is about 20%. So is it really, we really should be considering the surfactant a bit more than we do. It's not, it's more than just a surfactant now.
Okay, okay, thank you. So is there any other questions? So if not, let's thank Professor Iain McCULLOCH again for the very nice talk.
Oh, thank you again, Professor McCulloch. To express our appreciation, the PolyU Academy for Interdisciplinary Research make a small souvenir for you.
Thank you.
And I'd like to invite Professor Wang, Professor Tao, Professor Yang. Okay, come here to take a photo together. Yeah. Thank you again, Professor McCulloch. And I also wanted to thank all the audience here, and especially for those who ask questions to make this seminar even more interesting. So now I think this seminar is adjourned. Please stay tuned for our next seminar from PAIR. Thank you very much.